Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
Hello, everybody. Thanks for coming. My name is Bob Steagall, and I have the privilege of delivering several presentations in this year's Back to Basics track. Each session in the track is about a single concrete topic, like this one, which is an overview of the classic STL. And our goal with the Back to Basics track is to produce content that covers important things you need to know to be a working C++ programmer in today's world. And thanks to our Back to Basics track chair, Arthur O'Dwyer, who's actually sitting in the audience with us today, and John Kaub for making such a great conference. So, as I do with all my presentations, I'd like to start with a quick overview of what we're going to be discussing. The rationale for the STL, how and why it evolved, a little bit of history and a design overview. And then I'm going to talk about probably the three most important parts of the classic STL, and there are other things that are part of it, but these are the big three: iterators, containers, and algorithms. And really the focus of this talk, probably the majority of it, is going to be spent talking about iterators and thinking about iterators, because they're really the key, in my opinion, to the whole kit and caboodle. And in terms of the level of this talk, it's really intended to be C++ 101. I'm not going to make any assumption about what you know about C++. There isn't going to be any heavy template programming. It's starting from scratch, as if I were explaining these concepts to someone who might be taking a freshman or sophomore class in programming at university. So that being said, I'm hoping that when the talk is done today, you'll walk away with some slightly better understanding of the overall STL design, and especially understanding iterators and what they mean and how they fit into the library. And in furtherance of future understanding, I highly recommend these references. These are the ones that I look to first when I need to find something. Nico Jasutis' book, The Standard C++ Library, even though it's 9 years old, is still a very good, very relevant book. Effective STL is very old. It's 20 years old. But many of the concepts in the library are far older than that. And Scott does a wonderful job of explaining some very important and subtle points. Bjarne's book, his Intro to Programming book, Principles and Practice Using C++, also has a very good entry-level description of the concepts underlying the standard library. And of course, there's the old standby, CppReference.com, which I have open just about 24 hours a day in a browser. So what is the classic STL? Well, by my count, the C++ 20 standard has 16 chapters, 16 sections in the library. And the whole document is about 1,700 pages long. 450 pages of those describe the library, and it takes almost 1,200 to describe the library itself. But a lot of this is stuff that is more than what the original STL was. So if you had to categorize the original classic STL in terms of this, it would look more like this picture, where some of the utilities are split up into the original utilities that came with the library and the new generation of utilities. But mostly it's the containers, iterators, and algorithms. These are the major pieces that come from what we think of as being the original STL, or at least what I think of. And so original, classic. The short answer: containers plus iterators plus algorithms plus a few utilities. So what's the motivation for the STL? Well, at the risk of oversimplifying, actually I am oversimplifying, we begin with some business problem that we have to solve. And to solve that problem, as programmers, we start with some input data. We read that data in and we write programs to perform some sort of computation, some logic in the business domain. We generate some output and we write it somewhere. And this is really what our lives consist of. We take input, we do some computations, we write output. Well, To narrow it down just slightly from 200,000 feet to 150,000 feet, data is almost always collections of elements. We normally don't work with data about a single individual or a single thing. We work with data that's collections of tens or hundreds or millions of things. And there's a virtually infinite number of data element types in the universe. Each collection of elements that we want to work with has some representation. And by this I mean data structure, way of structuring these elements in a way that makes sense for the problem. And there's probably not an infinite number of representations, but there's a very large number of possible data structures and ways that you can represent collections of elements. There are many kinds of processing, many kinds of algorithms. There's a huge number of algorithms, far more than are even in the standard library. And so in any given problem space, there's not an infinite number of data types in a problem space, but there's probably a large number. There's not an infinite number of representations, but there's a good number. And not every algorithm is applicable. But there's still a number of types of elements, a number of types of representations, and a number of algorithms. And if you call them NT, NR, and NA for the number of types, the number of representations, the number of algorithms, in traditional programming, you kind of have a combinatorial explosion of choices of things that you may have to implement. NR times NT times NA. Well, we'd like a smaller number. Rather than multiplying each of those factors, it would be nice if we could add them together. And this is the number of things we have to worry about. And in one very real sense, this is the goal of the STL, reducing the space of possible things that we need to worry about building to a much smaller space, additive rather than multiplicative. So I wanted to do just a very brief history. In 1979, Dr. Alexander Stepanov began exploring what would come to be known as generic programming. And in 1988, he and David Musser published sort of a paper, which I think may be the first time the term generic programming was actually used. And this is the very first sentence of the very first paragraph of that paper. And what I think is very interesting about this is how well it captures what it is we try to do with generic programming and in C++. And just the bolded part of the sentence, abstracting from concrete efficient algorithms to obtain generic algorithms that can be combined with different data representations. If you think about what the STL does, if you know anything about it at all, that's what it does. And many years later, almost 20 years later, Bjarne was writing a paper, and he has this sentence in the paper, and I think it's also very telling. It's perhaps even a more concise description of generic programming, and that is lift algorithms and data structures from concrete examples to their most general and abstract form. And really the idea is we look at different concrete examples of some task we're trying to do, and we try to find commonality. And we use that commonality to abstract into a higher form, such that when we use that higher form for specific instances, we get the same or better performance than we did with the concrete representations that we were examining. So, going back to the history, in 1992, Meng Lee joined Dr. Stepanov at HP Research Labs, and his team was experimenting with C and C++ for the first time. He'd come from the world of, actually had done quite a bit of work in Ada earlier, and was able to implement some of his concepts of generic programming in Ada, but not to his satisfaction. So when he joined HP, he started looking at C and C++. At the behest of Andrew Koenig in 1993, he presented some of his main ideas at the November meeting of the C++ Standardization Committee. And they apparently liked it quite a bit. They asked him to come back with a proposal. In early '94, Stepanov and Lee presented their proposal for what would come to be known as the STL in the springtime meeting. And that proposal was actually accepted later that year. Of course, like everything the committee does, they weren't satisfied with it, and over the next 4 years, there was much more additional work that was done in refining the concepts, and actually, that was the time period in which the associative containers were added, and Dave Musser did that work. In 1998, we had our first ISO C++ standard published, and then, well, 13 years later, C++ 11 was created and had some new containers added after the originals. So Stepanov, at that first presentation, described his design principles. He wanted this to be a comprehensive library, extensible, efficient, natural. He wanted people to be able to add things to it, and he wanted the design of the components to be orthogonal and separate so that you could design one component like an algorithm without having to change another component like a container. In his abstractions, he did not want there to be any penalty for writing an abstraction. He wanted the use of abstractions to be as efficient as the concrete implementations. And actually at the bottom right there is a PDF that I found online from the original presentation, and if you look at it, you can see that I've actually shamelessly copied his bullet points into my slide. But these underlying principles are the ones that are still embodied today, and they're expressed in one form or another in almost every textbook. For my money, these are the things that are really the most important. The orthogonality of components. You can create an algorithm without changing a container and vice versa. Semantically based operability guarantees. And what that means is if you build a container and that container follows the rules for the interface that it provides and the way that it operates and the iterators that it provides, it'll work with the algorithms and vice versa. No penalty for generality. Complexity, runtime complexity is guaranteed and specified at the interface level. And it models, in some sense, the operation of a physical machine. Iterators are analogs to pointers. It operates at a level just slightly above the hardware, and that's how we get such good performance out of it. Now, probably you've all seen big O notation, but in my travels and the companies I've been at, it surprises me how many people are unfamiliar with it, and I'm going to use it a little bit. So I thought I'd provide a background slide here. So complexity, as I mentioned before, I'm defining it as the runtime cost of an algorithm, and big O notation is a way that we use in computer science to express the relative complexity of an algorithm. So here's a little table of various kinds of big O notation. And the important ones for the purposes of the standard library are constant, logarithmic, linear, n log n, and quadratic. And what that means is the amount of time something takes relatively has that sort of time complexity. Something that it runs in constant time is independent of the number of elements, like adding an element onto the end of a doubly linked list. Logarithmic time might be like searching for an element in a balanced binary tree. It takes log n, the number of elements, to find the thing you're looking for. Linear means that it's proportional to the number of elements. Searching linearly through a vector is a linear operation, and so on and so forth. So there are, besides the design principles, there are what I think of as key principles in how the classic STL was put together. So we have containers, and containers are these data structures that store collections of elements. We have algorithms, and algorithms perform operations upon collection of elements. Notice I didn't say that algorithms perform operations on containers. You can have collections of elements that are not actually in containers, right? Like reading from a stream or writing to a stream. You can abstract a stream or a socket or a file as being a container, as being a collection, but not necessarily being a container. So containers and algorithms in STL are entirely independent. The algorithms have no knowledge of the containers, and the containers have no knowledge of the algorithms. And then we have iterators, which I think are the key insight of the STL, because these are things, abstractions that provide a common unit of information interchange between the containers and algorithms. Iterators are what allow algorithms to use the data that's stored in containers. Iterators are the things that allow containers to provide their data to algorithms. So for my money, again, these last 2 points are the most important. The independence, the orthogonality of containers and algorithms, and the fact that iterators are this common unit of information exchange between those two things. So the STL makes complexity guarantees by specifying interfaces and requirements. And so the containers provide support for all of these operations, adding and removing elements, accessing and reading elements, providing iterators, and the iterators that a container provides understand that container's internal structure and how to find and access the elements inside that container. They abstract the internal structure into a form that the algorithms can use. And as I said in the previous slide, iterators provide access to a container's elements, and they do that using a well-defined interface, such that container or algorithms don't need to know specifically what the iterators are. They can be written in terms of generic iterators. All of the algorithms are, for the most part, function templates, and they're parameterized in terms of the iterators, which are used in their arguments when you call them. Not specific iterator types, but generic iterator types. And the algorithms, they use the interface provided by the iterators to do their work. So the iterator provides sort of a middleman between the algorithm and the container. And the complexity of the overall operation is based on the algorithm itself and the guarantees that are made by the containers. In one sense, the containers or the iterators constrain what algorithms can do, and we'll see why in a few slides. So containers represent collections. We have a wide variety of containers. They employ a wide variety of basic data structures like you'd find in Sedgwick or Corman or Knuth or any of those. But at the heart of it all, each STL container represents a sequence of elements. All of the containers have an internal structure and ordering as it makes sense, and we can observe this ordering. Sometimes we can even control the ordering, but not always. In fact, the majority of the containers, we actually don't control the internal ordering. The way that the container itself operates manages the ordering. We can observe the ordering, but we can't always control it. Most importantly, containers own the elements that they hold. And ownership means, of course, that they manage the lifetime. Containers are responsible for constructing and destroying the elements that are stored within them. So quickly, we have an overview of the containers we have. We have the sequence containers. And these are containers, here sequence is used as an adjective. Sequence containers are the ones whose orders that we can observe and we can modify. And they have different properties, different time complexity properties on how they manage elements. We have the original associative containers, and they have an ordering, and they manage the ordering internally. We have map, set, multi-map, and multi-set. We have the unordered associative containers, and these came in with C++11, and these are essentially implemented by hash tables. So the hash function manages the internal ordering. We can observe the ordering, but we can't change it. And then from the original classic STL, we have container adapters. We have queue, stack, and priority queue, which are essentially wrappers around some concrete containers that provide the necessary runtime properties. So iterators provide a way of observing a container's elements and its ordering, and some containers provide more than one way to observe its elements, and we'll see that in a few slides. Iterators may provide a way of modifying a container's elements. Most iterators only provide const access or read-only access to elements, but there are some containers and some elements that allow you to modify the contents of elements. The iterator's interface specifies things like the complexity of observing and traversing the collection's elements, the manner in which elements are observed, and whether or not an element can be read from or written to. But it does this in an abstract way such that iterators have a well-defined interface that's used by algorithms in order to perform the computations I mentioned earlier. And the converse is of containers owning elements is that iterators never own the elements to which they refer. They are, in a sense, pointers. They are conceptual pointers. Sometimes some older containers, older implementations of vector, for example, used to actually use raw pointers as iterators. So pointers are actually implement the random access iterator interface. So we have 5 iterator categories in the classic STL: output, input, forward, bidirectional, and random access. And these things, you'll see this diagram if you read books, read references on STL. These are arranged in a hierarchy of requirements. So the arrows in this case do not mean public interface. What they mean is, they don't mean that, for example, a bidirectional iterator is publicly inherited from a forward iterator. Instead, what they mean is that, for example, a bidirectional iterator implements all of the interface that's required for a forward iterator and some more stuff. So it's in a sense, inheritance of interface, not inheritance of implementation. So the algorithms, as I mentioned before, they process ranges of elements in a collection, and all of the algorithms require at least one explicitly specified pair of iterators, and we'll see why in a few slides. And we have a number of categories of iterators. And the categories I'm about to show you aren't actually part of the standard. They come from Nico Jasudis' book that I mentioned in that early slide. We have non-modifying algorithms which access elements without changing their order, searching, counting, min, max. We have modifying algorithms which can change the value of elements in a sequence, either in place or by modifying and copying into another container. We have removing algorithms, and these are things that remove elements from a sequence. And all of the removing algorithms actually work by rearranging elements in a sequence so that the removed elements move to the end of the sequence in a way that they're not seen anymore. We have mutating algorithms which can actually change the order of elements but not their values, things like reversing or rotating or permuting or shuffling. We have the sorting algorithms. We have sorted range algorithms. And then last but not least, we have the numeric algorithms. So let's talk about iterators. We've got the 5 categories of iterators, and it's legitimate to ask yourself, where do the 5 categories come from? What interface does each category provide? What is the time complexity associated with iterators and the operations they provide? How are they related to containers? How are they used by algorithms? I'll try to answer these questions in some level of detail. Probably not as much as you would like, but as much as time permits. So let's try a generic programming exercise and develop iterators from scratch. Let's go back to the early 80s and think about what programmers had available to themselves at the time, right? They didn't have templates. They had C. So let's think in terms of C and the C facilities that were available in the mid and late 80s. So let's think about referring to elements in an array. Suppose you have an array and consider you have pointers to 2 elements in an array of n objects, right? What can you do with those pointers? Well, here's a table of things that you can do. You can access elements, you can access members of elements, you can compare for equality of position, you can move forward by 1 with pre or post increment, you can move backward by 1, you can make a copy of a pointer, you can access an arbitrary element through indexing, you can move forward and backward by an arbitrary amount, you can compare 2 pointers for equality, you can compare 2 pointers for relative position as long as both pointers point within the same array. And the interesting thing is that all of these operations have constant time complexity. They're all order 1 operations. So this is interesting. This is a concrete example of a kind of iteration. Consider elements in a doubly linked list, right? Suppose you have a doubly linked list and you've got pointers to 2 nodes in that simple list. What can you do with them, right? Well, here's another table. You can access elements, you can access members of elements, you can compare pointers for the pointers for equality of position, you can move forward and backward by 1, and you can make a copy of a pointer. Now, as we all know, with doubly linked lists, you can't randomly access them, but you can move backward and forward in increments of 1. All right, this is interesting. This is another kind of iteration. And all of these operations also have constant time complexity. Now let's think about singly linked lists, right? Consider a singly linked list where you have pointers to 2 nodes in that list. What can you do with them? Well, you can do a little bit less. You can access elements, you can compare for equality of position, you can move forward by 1, but not backward by 1, and you can make a copy of the pointer, right? And these are all constant time complexity. All right, so you can, if you think about it, this is kind of beginning to fit into those 3 of the 5 categories we saw in that diagram. Well, all of these 3 data structures that we just looked at all support the idea of multipass iteration. In other words, you can have pointers to elements, and those pointers can be dereferenced as many times as you like, and as long as the element hasn't changed and the pointer hasn't changed and the pointer still points to the element, every time you dereference the pointer, you'll get the same result. And the sequence can be iterated over with pointers multiple times. The act of iteration does not change the sequence itself. But those are not the only kind of sequences that we're interested in. What about sequences that can only be traversed 1 time? Some sequences only support what you can think of as being single pass iteration. For example, reading from a file or reading from a socket. You can consider the bytes that come out of the socket to be a sequence, but the act of iterating over that sequence changes it. You can't, you could copy a byte from a buffer and dereference the byte multiple times, but you can't dereference random locations behind the socket. The act of reading from the stream of bytes that the socket represent irrevocably changes the state of the stream. So let's think about reading bytes from a file stream. And here on the traditional C file structure, right? You have a file pointer, you open it, you get a pointer to the file structure, not to the bytes, but to the file structure, which is a struct that the C library makes for you behind the scenes. It's a black box that you can't peer into. So what can you do with this? Well, you can read an element from it, and the act of reading an element advances the stream pointer to the next location, which has not yet been read. You can compare the byte that comes out of that when you've opened a file for the EOF byte, which the library will provide for you when it gets to the end of the file. When you get to the end of the file with C, it will provide a -1, an integer -1, and you can compare the byte that you've read to see is that what you've received, and if so, you're at the end of the file. And you can make a copy of the file pointer, right? These operations are, in a sense, constant time. The act of actually reading that byte may take a very long time, but it's the same amount of time every time you read the byte. What about writing bytes to a file stream? Well, consider a file stream that you've opened for output. You've got a file pointer. What can you do with it? Well, you can write the element, and that advances it, in a sense, in the file stream to the next unwritten location, and you can make a copy. But when you write to a file stream, there is no EOF, there is no end. It represents, effectively, an infinite sync. These operations are also constant time. So now if we think about those operations, and we think about our category of iterators, there's kind of a mapping here. Output iterators correspond to sort of a write-forward, single-pass mode of operation. Input operators are read-forward, single-pass. Forward iterators represent accessing forward, multipass, bidirectional, accessing forward and backward, multipass, and random access, accessing arbitrary positions in multipass. So from top to bottom, writing to a file, reading from a file, iterating over a singly linked list, iterating over a doubly linked list, or iterating or randomly accessing a vector. So those concrete examples, I like to think, are the sorts of things that they had in mind when they abstracted those examples to design the interfaces that the 5 categories of iterators express. And as I mentioned before, these are arranged in a hierarchy of requirements, not public inheritance. An arrow to X means this thing, bidirectional, satisfies at least the requirements of forward and more. The dotted arrow in the diagrams means optional. All of the iterators on the right, input, forward, bidirectional, and random access, they all provide read access. Forward, bidirectional, and random access iterators that allow you to write also implement the interface of output operators. Since input iterators are read-only, they cannot and do not implement the interface of output iterators, which are write-only. And finally, you may hear the term mutable iterators, and mutable just means this iterator satisfies the output, or satisfies the interface for output iterators. So let's think about sequences then. Think about sequences in terms of positions. By fiat, let's say that a sequence of n elements has n plus 1 positions in it. And the first n positions of that sequence contain elements and they are dereferenceable. We can refer to them, we can dereference them, and by dereferencing them, we can read the values of those elements. And we will assume that the last position contains nothing. There's nothing there to be dereferenced, and dereferencing that is an illegal or invalid operation, and it's therefore non-dereferenceable. You can refer to the last position, but you cannot read to it or write from it, write to it or read from it. So in STL, we iterate over sequences based on the idea of iterator ranges. And an iterator range is represented by a pair of iterators, which are traditionally called first, last, begin, end. We'll call them first, last here. And so it's a half-open interval. If you remember set theory from high school a long time ago, it represents a half-open interval over this sequence of elements. First refers to the first element that's included in the sequence, and last refers to the non-dereferenceable one past the end element that is excluded from the sequence. So why do we use ranges that are described by half-open intervals in this way? And the answer is it makes testing for loop termination very simple, and there are also some abstract algebra reasons if you read Stepanov's book that he goes into, but for the purposes of this, it makes iteration over sequence ranges dead simple. Loops only need to test for the equality of iterators to know when the loop is terminated. There's no indexing involved, so therefore random access is not an issue. And the location in memory of the thing that the iterator refers to is irrelevant. And so here's a little code sample to sort of give you the idea. You know, we have our first and last iterators, and here is just some pseudocode for some functions that get the position of the first element in the sequence, get the position one past the end in the sequence, and then here's the loop. You just run over the loop until f equals L, you increment f, and while you're in the loop, you do something with the thing that f points to. It's that easy. So how can iterator ranges actually work in practice? I've done a little bit of hand waving here. How are iterators and containers actually implemented in the real world so that this idea of half-open ranges can work? Well, it depends on the container and the sequence. Containers that store their elements contiguously in memory, i.e. vector and array, rely on the ability to always get a pointer to the next location in memory after the last element in the array. And the standard guarantees that that can be done. So the pointer, an actual physical pointer to the memory location after the end of the array is what represents the next position after, the past the end. So here we've got a single object, and we can get a pointer to it, and we can get a pointer to the memory location immediately after that object. And so in this particular example, our iterators, we're using raw pointers as iterators, so our begin pointer is the element, and our end iterator is the memory location immediately after that object. For arrays, it's a very similar principle. Our begin iterator is a pointer to the first element, and our end iterator is a pointer to the memory location after the last element in the array. Node-based containers can use sentinel nodes, and a lot of STL implementations actually use this. So here's an example of a conceptual diagram of a doubly linked list that uses a sentinel node. So here our begin iterator is pointing to the head of the list, and our end iterator is pointing to the sentinel node. And here I've attempted to denote that these elements with this green are containing elements, or these nodes are containing actual data, and the sentinel node has nothing there, so it can't be dereferenced. But the sentinel node conceptually represents the memory location past the last element. And you can also have sentinel nodes with singly linked lists in the same way. And with binary trees and multi-way trees, you can use sentinel nodes as well. Any container that is based on nodes, you can devise a form of iteration over that container using sentinel nodes so that you can form an iterator range pretty easily. So now let's build up the iterator interfaces from bottom to top. Let's start with output iterators, which are write forward single pass. So here's a little table of their capabilities and the interface that the standard guarantees that they provide. You have copy construction, copy assignment. You can write to a position one time. By accessing and dereferencing the iterator, you can use that dereference one time. And you can step forward, returning a new position, or you can step forward and return an old position. The only valid use of the dereference is on the left side of an assignment statement. Comparison operators are not provided for the output iterator interface because there's no conception of the end of sequence. They sort of model the idea, as I said before, of an infinite sync. And by the by, const iterator types that are provided by our STL containers cannot be output iterators because they only permit reading, right? Correct? So input iterators, and as you'll see as we go through this, the tables start getting longer. These are read forward single pass. And so they provide for the same things that the output iterators provided for. Read access to elements by dereferencing on the right side of assignment operators. You can move forward and backward, and you can compare for equality, but there's a caveat. Two input iterators that are not past the end iterators can compare equal only if they refer to different cannot compare equal if they refer to different positions. The only time that two input iterators that compare equal are actually guaranteed to point to the same thing is if they both point to the past the end iterator. So P equals Q does not imply and does not guarantee that incrementing P and incrementing Q get you to the same place. So all iterators that read values must provide at least the interface that you see here, and usually they provide more. Now, the output and input iterators are only single pass iterators. When we get to forward iterators, things start getting interesting. Now we can access elements as many times as we like. We can move forward by one, and with forward iterators, we're guaranteed that whether we're pre-incrementing or post-incrementing, we're going to get the new position in performing that operation. We can do comparison of iterators, and it means what you would think it would mean. In the case of forward iterators and beyond, if P and Q refer to the same position, you're guaranteed that P will compare equal to Q. And if P equals Q with forward iterators, this also implies that incrementing P and incrementing Q gets you to the same location. Accessing an element with a forward iterator doesn't change the iterator's position, which is important for iterating over containers. Bidirectional iterators add a little more capability, the ability to move forward and backward by 1. And so here, if P equals Q, this implies that you can decrement both of them, and they'll both point to the same element, assuming there's an element behind them, and that if you increment an iterator and then decrement it, you'll be back at the same location as if you had not changed the iterator. Random access iterators add even more, and the table continues on the next page. And these things really very closely emulate raw pointers. They provide additional capabilities for random access, for being able to move to locations randomly, or arbitrary locations in constant time. They provide for the same equality and inequality operators, but they also provide comparison operators for ordering, so that you can tell whether the element that P points to precedes or succeeds the element that Q points to. And as long as P and Q point to elements in the same sequence, comparing P and Q for equality is a valid operation. We also have the concept of iterator adapters, which provide additional functionality beyond iterators themselves. We have reverse iterators. And reverse iterators are typically implemented with a kind of container that wraps an iterator type. And so it works for bidirectional and random access iterators. And what it does is it's designed to iterate backward from the end of a sequence to the beginning. So iterating a reverse iterator forward actually moves you backward in the sequence. And so if the underlying iterator type that it wraps is a bidirectional iterator, then the reverse iterator itself will be bidirectional. If the underlying iterator that it wraps is a random access iterator, then the reverse iterator will also itself be random access. We also have insert iterators, which you will often hear referred to as inserters. And there's the back insert, front insert, and general insert operator. And these are things that model an output iterator, and they're designed to insert elements at the back, the front, or the interior of a container, respectively. So let's talk about containers. We have the sequence containers. They're ordered collections of elements. The important thing is that the element's position is independent of its value, and these are usually implemented with arrays or linked lists, and I'm using array here in the sense, the classic sense of a contiguous sequence of elements in memory. And these are modeled by vectors, decks, lists, arrays, and forward lists. We have the associative containers, and these are sorted collections where an element's position depends only on its value. And you have to be able to provide some sort of comparison, some strict weak ordering comparison operation so that the elements in these containers can be sorted. They're usually implemented using binary search trees. All of these standard library implementations that I'm familiar with use red-black trees, if you know what those are. And map, set, multi-map, and multi-set are the containers that provide these facilities. And we have the unordered associative containers. These represent unordered collections in memory. In this case, the ordering and the position of the element is irrelevant. What is important is the access time in being able to retrieve an element. These are, even though they're called unordered, they're actually all implemented with hash tables. And in fact, the hash function that you use is one of the template parameters that you supply to one of the unordered containers when you instantiate it and you want to use it. So all of the STL containers, every one of them provides a common set of nested type aliases. And they do this so that if you do vector of T : iterator, or list of T : iterator, or container of T : iterator, there's always that nested public type def iterator, which allows you to know what the type of the iterator is that goes with this container in a generic fashion, right? So this is not the entire collection of nested type defs, but you have value type, which represents the kind of element that the container is storing. You have reference and const reference, which are, if the container is storing type T, are tref and tconstref. Then, for our purposes, you have iterator and const iterator, providing iterator provides read and possibly write access. Const iterator provides read access. Size type is an unsigned integer type which is capable of representing the number of elements that the container can possibly hold. Difference type is a signed integer type which is capable of representing the distance between two iterators in the sequence. And it has to be negative because you can have a negative distance between an iterator further than a sequence with an iterator near the beginning of the sequence. So distance can be positive or negative. Every STL container also provides a common set of functions. You have begin and end, which non-const begin and end, which return iterators. You have const begin and end, which return const iterators. And you have cbegin and cend, which were added, I think, in C++11, which return const iterators. And the C in the name obviously means const. Every bidirectional container and above also provides additional aliases and functions. They provide reverse iterator and reverse const iterator, or const reverse iterator, because they have to provide iteration from back to front. And like the other functions, you have rbegin and rend, which return reverse iterators, which provide read and possibly write access. You have rbegin and rn, which return const reverse iterators for read-only access, and crbegin and crn, which are equivalent to rbegin and rend. So every container will have those nested type defs and nested functions that I mentioned 2 slides ago. Every bidirectional container will also have these functions. So I'll quickly go through the catalog of containers and the differences. So we have vector. And the interface for vector looks like this. There's a declaration at the top. And here are, I'm not going to read all of the features here. I'm going to try and get to the important ones. The important thing with vectors is it stores its elements contiguously in memory. It provides amortized constant time insert and erase operations at its end. It provides constant mutable random access iterators. It provides constant mutable element indexing. You can change the order and the values of elements, and it uses contiguous storage, as I said earlier, for everything except bool. And their opinions on the utility of vector of bool vary quite a bit. You have dec, which conceptually represents a container that has random access semantics, but can be extended in constant time on either end. Now, decs don't have to store their elements contiguously, and they often don't. The picture that I have here on the screen is a conceptual picture only. The underlying implementation for decs is usually quite a bit more complicated than this. They have very similar properties to vectors, the difference being you can also add to the beginning of a dec, and they support random access semantics. You have arrays, which were added in C++11, and you'll notice that they are not parameterized in terms of an allocator because they are fixed size structures. And they represent a fixed size sequence of elements that is stored internally, effectively, in a C-style array. It instantiates, or it constructs all of its elements when it's instantiated, just like a C-style array. It provides const and mutable random access iterators, but you can't change its size. The size is fixed. You have the old school container called list, which everyone implements as a doubly linked list. It provides const and mutable bidirectional iterators. You can change element values. Interestingly, it provides functions for splicing and sorting and merging as member functions. The cool thing about splicing is you can take 2 lists and you can splice, you can take all of the contents out of one list and splice it into another list, and that's a constant time operation. So occasionally you need to do that, and that's a very cool feature. right? If you think about how to manipulate the pointers that represent the nodes in a doubly linked list, and you know the number of elements in each list, then you can see how splicing one list into another is a constant time operation. We have forward list, which is really a singly linked list. It only allows you to iterate over it in a forward direction, and it also will allow for splicing. We have set, and here it's an associative container, so it's parameterized in terms of a key, which is the value type that it's storing, a comparator type, which is used to do the ordering of the elements in the tree, and of course it's a dynamic container, so it also has an allocator as a template parameter. It allows you to find things in logarithmic time, and the elements, as I said, are sorted according to the relationship that's provided by the compare template argument. It provides const bidirectional iterators, so you can actually start at the leftmost leaf and iterate in a linear, iterate forward to the past the end iterator here, or you can start and you can iterate backward over the tree. And I can't do it precisely with the pointer here. You have, the important thing about maps is that the keys, wrong way. The important thing about sets is that the keys in the set are unique, right? There's only one, if you're storing integers, you can only store one key of 10, for example. Multiset is basically identical to set, except it allows you to have non-unique keys. Then you have map. So map actually sorts its elements. Its elements that it keeps are a pair. The element is a pair, and the pair contains a constant value of key and a value. And so it's parameterized in terms of key and value. It has a comparator that sorts those pairs in terms of the key. So everything is sorted by key, and the keys are associated with values. So like the other two, logarithmic lookup time, key values are unique, and it supports bidirectional iteration. And it's typically used as an associative array. In fact, it provides brackets syntax like similar constructs in Python or Perl, for example. Multimap is the same as map, except it allows for keys that are not unique, and you can use it as a dictionary. And the analogy with dictionary here being that you can have multiple definitions for a word. Well, you can have multiple values of a key, and each key representing a word has a different definition. We have unordered set, and here the template, the class interface is even more complex. You're storing a key, you have some hash function, you have another function that tells you when two keys are equal, and because it's a dynamic data structure, there's an allocator associated with it. The important thing is that it supports constant time element lookup because it's a hash table, that's what it's designed to do. The element values are unique, and it must provide at least forward iteration. You can iterate over all of the elements that are stored in an unordered set. And as long as you've not changed the contents of the set, that sequence will be the same. But if you add an element to an unordered set, there's no guarantee that the portions of the sequence, any portion of the sequence will be the same as the iteration you just did. We have unordered multiset, which is the same as unordered set, except it allows for non-unique keys. We have unordered map, and again here, it's the same principle as the ordered map. Its elements are a pair of key to value, so it's parameterized in terms of key and value. It hashes the key, and to compare for elements for equality, you have a comparator that tells whether two keys have the same value. So keys are not unique, and it must provide also at least, keys are unique, and it must provide forward iteration. You have unordered multimap, same as unordered map, but keys are non-unique. And then you have the container adapters. And just like you had the iterator adapters, you have container adapters. You have stack, which can wrap vector, deck, list, and forward list. And it doesn't provide any real interface to it other than the classic push, pop, and top operations in the classic stack data structure. And so it requires from its container, so it's parameterized in terms of the element type and some container. And its requirements are from container is that it has constant time pushback and pop back member functions and a constant time back member function to access the element which is at the top of the stack. You have Q, very similar, parameterized in terms of an element type and some underlying container. It is a wrapper that implements a classic FIFO queue, and it provides for constant time push and pop operations. So you push things onto the back of the queue and you pop them off the front. And it will work with vector, deck, list, and forward list. You have priority queue, which implements a classic heap data structure. It has logarithmic time push and pop, but it has constant time access to the next element in the sorted sequence with its top operation. And it's implemented in terms of containers that provide random access iterators, vector and deck. There's a large number of algorithms that are provided by the STL, well over 100. I tried counting them, and I couldn't figure out how to count them exactly. A couple years ago, Jonathan Bakar had a talk entitled 105 Algorithms in an Hour. I'm not sure how he managed it, but there's at least 105. For each of them, there are multiple versions of almost all of them. For some of them, they have parallel implementations. And because this is classic STL, I'm not even counting the re-implementation of those in the ranges library. For reference, I've included the algorithm categories that we discussed before. And I thought what I would do is show a couple examples of reference material about about 3 different algorithms and sort of explain how to read them. So for example, let's look at sort. And if you read CppReference.com or you read through the standard, it will tell you what sort does. So here we've got our half-open range of iterator range. And it will sort things in non-descending order, meaning that for any given element, it's guaranteed not to be less than the element that precedes it. You can provide a comparison function to it. Its time complexity is guaranteed to be at worst n log n, where n is equal to the number of elements in that range. And what I wanted to do is just provide the prototype, the declaration of the function here. Often when you see these declarations, you can infer what it is that's required because of the way they write them. So you can see that sort requires random access iterators, and this particular version uses a comparator. Now, there's no requirement here in the sense of concepts providing constraints. It's just a convention that's used so that you can quickly understand the facilities and the requirements that a container provides. Here's lower bound. Lower bound returns an iterator pointing to the first element in some range that's not less than some value that you're comparing it to. And I thought this was interesting because it's doing searching, it's doing binary searching, but it actually works with forward iterators. And you would think to do binary searching, you would want to have random access iterators, but no, it's actually, you can write it in terms of forward iterators. And what I think is interesting, at least from this context, is the way the complexity is described. So the number of comparisons performed is logarithmic in the number of elements, right? That makes sense. But there's this footnote that says, for non-random access iterators, the number of iterations, the number of increments, the number of movements through the container is actually linear. So I thought that was kind of interesting. And finally, a sample of remove copy if. And this is actually very similar to the original example that appeared in papers and presentations that Dr. Stepanov gave many years ago. And this is an algorithm that removes elements from some range if an element fulfills some criteria. And so I just provided this because I thought it was interesting. This is parameterized in terms of an input iterator, an output iterator, and some predicate. And it returns an output iterator. So it's over this range of input from first to last. I'm going to copy things, except I'm going to remove stuff that I don't like, and I'm going to use this predicate. And so the loop is really simple and easy to understand. I'm iterating over the range. I'm looking at the elements to see if my predicate decides whether or not it belongs. And if my element doesn't meet the predicate, then I keep it. Otherwise, I skip it, right? It's very simple. So in summary, and I'm a little bit over time here, the key principles, just to reiterate: containers store elements, algorithms perform operations. Containers and algorithms are entirely independent of each other. Iterators provide a common unit of exchange between the two. And finally, STL makes complexity guarantees by specifying interfaces and requirements. And so I will leave it at that. Thank you, everyone, for coming. Sorry for running over a little bit there.